Okay, so we're going to start this video in exactly the same place that we left off the previous video. We've just opened up task 15, which is calculating the EVPI, or expected value of perfect information. And on the incremental net monetary benefit sheet, you'll see that there's another column that's appeared. And there's two ranges. The first is for the value of perfect information, which we calculate for each iteration. And then there's the EVPI, the expected value of perfect information, which we take by averaging over the value of information, the value of perfect information for each iteration. Okay, so I'll let you read these paragraphs on why we would consider EVPI, why it's important. Let's go on to step 15.1 and start calculating this. And in order to calculate the EVPI, we need to calculate the VPI for each iteration first. And so, as it mentions here, you can make wrong decisions in the presence of uncertainty. And so I'm going to let you read. There's a lot of text here. I'm going to let you read this. But what we need to do is write a formula in cell BO38 that encompasses the logic of these paragraphs above, and calculates the VOI for iteration 1, and then that's going to be copied down to the other iterations. Okay, so let's look at this to recap. So if the total incremental net monetary benefit for an iteration is positive, right? So if this were positive, this cell here, BM38, and if the average over all iterations is negative. So if this average here were negative, which it is, right? That is negative. Imagine for a moment that this was positive, okay? Well then, what does that mean? It means if this iteration, out of all 1,000 iterations, if this iteration were actually the closest to being the truth, yeah, the true, it has the true values of each of the inputs, and that is the true output. If that were the case, well then, if this were actually positive, then treatment B is cost effective. However, we don't know that this iteration is the truth. Any of them could be. And so we go with our expectation, which is negative, and we say that treatment B is not cost effective. Okay. So in that case, our uncertainty would have caused a problem if this were positive. And if the signs are reversed, right? But it says, but if the signs are reversed such that the total incremental net benefit, for an iteration is negative, which it is, and the average is positive, okay, well then we also have an issue, right? Because treatment B is not cost effective, but we would expect that it is. So an issue arises whenever the average over all of these iterations, which is in BM33, is positive, but the total for any particular iteration is negative, or vice versa. That's where we have a problem, because it means that if that iteration actually is the truth, well then we're going to make the wrong decision by basing decisions on the expectation. Okay, so we need to then calculate what the loss is in net monetary benefit if we were to make the wrong decision on that particular iteration. And to do that, we just need to take the absolute value of this value here. So if this were positive, well then we would be missing out on 23,762 if it were positive. That we'd be missing out on that incremental net monetary benefit if that was the truth, and if we made a decision based on the average, which is negative, right? We would go with treatment A, and we're actually going to lose out on $23,782 of incremental net monetary benefit. If this is negative and this is negative, well then, and then this is the truth, well then actually we're not missing out on anything, because in the presence of uncertainty, we think that treatment B is not cost effective, and you know what? It actually isn't. So in that case, the value of perfect information would be 0. So we want this cell to be 0 if these two things have the same value, but take the absolute value of this cell if they have different values. Okay, so how can we do that? Let's have a go at that. So there's a sign function that might be helpful, and the if statement, the if function. So let's say equals if the sign, and you can see sign there, sign of the provided number, it's either positive, negative, or 0. If the sign of this cell here, and I'm going to close the bracket, so that is positive or negative, right? It's very unlikely to be 0, equals the sign of this one here, right? So BM33. So if those two signs are equal, then I want this cell to just have the value 0. There is no value of perfect information for that particular iteration if the signs are equal. But if that's not the case, then we need to take the absolute value of BM38. So we'll use the ABS function, which is absolute value. And we're going to click again on this cell. We just need to close the bracket. And then we need to close the bracket that's around the if statement. Now, before I press enter, let's think about this. This is going to get copied down. As it gets copied down, I want the BM38 to change to BM39, BM40, but I don't want the BM33 to change to BM34. I want it to stay as BM33. So I'm going to just put a dollar symbol before the 33. And then I think that looks good. Let's try that. Now, here's the funny thing. All of these are negative. So I expect this to be 0 for these first 10 iterations. But I'm sure that somewhere among the 1,000 iterations, there must be at least a few that are positive. So although these are 0 for these first 10, if we were to scroll down, no luck so far. Oh, did I see something? No. Oh, there we go. On this iteration, it was positive. So we have correctly pulled in 2,433. If this iteration, which is in row 415, it's actually iteration number 378. If that happens to be the truth, and of course this iteration has exactly the same probability of being the truth as all of the other 999 iterations. If that was the truth, then we are losing $2,433 in incremental net monetary benefit by going with the average, which is negative. And we're saying treatment B is not cost effective. Actually, if this is the truth, well, then it actually is cost effective, right? We're making the wrong decision. But given this, given all of the inputs to our model, given a $50,000 per quali cost effective threshold, it is very likely here that treatment B is not cost effective. See, look, there's another one here where treatment B is cost effective, only a little bit, $278. That's what we're losing out on by if this iteration were the truth. If it were the truth, that's what we're missing out on. Okay, now, if we come back to the top, we need to do step 15.2, calculate the EVPI by averaging the VPIs across all iterations. So we just need to take the average of all of these. So equals average, and we'll do this one, hold down Control Shift down to this one, and it's $10. Okay, so most of them are 0, but the mean is $10. So there is very little value right now, given the parameters in our model, given the settings in our model, very little value in getting perfect information. Okay, there's a very small chance that treatment B is cost effective. And so if there were a trial, hypothetically, that could get us perfect information about all the parameters in our model, which of course doesn't happen in reality, but imagine that there was, well, then it would be worth $10 to us for this decision. Okay, so it's probably not worth conducting any further research to inform this particular decision. Of course, trials can have value in other settings, but for this particular decision, it probably isn't worth waiting to conduct further research to resolve the uncertainty in our model. Okay, it does say optional, switch to the setting sheet, increase the threshold to 100,000. Okay, let's try that. So on the setting sheet, we can change this to 100,000. Take a look on the right. When I change this, have a look at these values here, and this value, and also these estimates here, and of course the EVPI. Take a look at those when I change the threshold on the left to 100,000. Okay, it's going to take a second or two for the model to recalculate. You can see that. And suddenly things are now interesting with this much higher threshold. Just ignore that that says that that's red. Of course, that is the incorrect value for now. Just ignore that for now. So the EVPI goes up to $5,251. And that's because there's actually quite a few iterations now where we have a conflict between the sign for that iteration and the sign on the average. Okay, and for those, you know, right now at $100,000 per quality, treatment B does appear cost effective on average. So given our expectation, we would recommend treatment B. However, on lots of these iterations, actually treatment B is not cost effective. And so there would be value in getting perfect information, which would allow us to determine which of these 1,000 iterations is closest to the truth. And if it happens to be any of these ones where the incremental net monetary benefit's negative, well then getting that perfect information would have saved us from making a wrong decision. And there's value in doing that. Of course, there's also iterations where we're making the correct decision. And so even if we had perfect information, we'd still go along with treatment B. And so the expected value of perfect information is just the average over these. And now it's gone up to $5,251. So at a willingness to pay threshold of 100,000, there's greater uncertainty about our decision, or to put it another way, the value of that uncertainty, of resolving that uncertainty, is now much greater. Okay, we're going to put this back to 50,000. And then go back to the instruction sheet. And we will tick this box to say that we're finished. And that brings us to the end of task 15, and I'll see you on the next video for task 16.